Got it? Okay, let's begin with a word of prayer. I will start. Dear Heavenly Father, we thank you for this weekend just completed. I just thank you again, Lord, for these students. Just pray with us today. Help us to just wrap up any questions they have about their homework. Pray that they would get the most they can out of this class, Lord, as they try to just learn this material the best they can, Lord. We just pray that whatever we do today, Lord, we do it for your glory. In my prayer, Lord Jesus. Amen. Before I take any questions, let me just make a few comments. First of all, obviously, there's like a little bit of a formatting problem with problem 33. Basically, there's two questions there. So let's say you got part A and you got part B, right? So for problem 33, let's just say problem 33, part A would be to let f of xy equal the square root of x squared plus y squared, and then find the domain of f and where f is continuous. And then part B is to let f of xy equal to sine of x squared plus y squared divided by x squared plus y squared for xy not equal to 0, 0, and f of 0, 0 equals to a, and then choose the appropriate value for a such that f is continuous on R2 and show relative to the choice that f is indeed continuous on R2. So that's how 33 was meant to be understood. It's a two-parter. The first part is easier than the second part, but whatever. Let's see if I have anything else to say here generically. Nothing else sticks out at the moment. I'll let you guys ask questions then.
35B. What is that supposed to say?
35B? What do you mean, what is it supposed to say?
On mine, after the plus sign, I opened it with Adobe and that's what it gave me.
Yeah, that's not wrong. What's the problem? I mean, let's see here. So 35B, just to clarify the notation, since there's a question. I do not have it memorized. In just a second. So we've got the hyperbolic cosine, or cosh as I affectionately refer to it, of x squared times y plus y divided by the exponential of x plus y squared. Now, another notation for this would be the following. Cosh of x squared y plus y e to the minus x minus y squared, if you like, as 1 over e to the u is equal to e to the minus u. And by the way, e to the u is also denoted exponential of u. So the exponential is just the exponential. It's just sometimes we write exp as to put it in a bigger font, mostly. I mean, so it's not a superscript, so you can see the argument easier. The intent there was not to confuse. But anyway, this is part of math, right? Getting used to different notations. So, other questions? 16.2, number 37. To me, there's one thing as I was looking at the problem mission, there's one thing that sticks out to me as something I haven't actually done in class, but we'll get to that, I'm sure. Let's see here. But your question is number 37. The temperature in a neighborhood of the point is given by blah. Find the path followed by a heat-seeking particle. This is a question that's essentially about finding an integral curve. Let me explain. So you've got the temperature, it's number 37, of section 16.2. Actually a very interesting problem. And so I'm not sure how hard it is. Let's see here, t of xy, without getting into it. So it's square root of 2, right? E to the minus y cosine x, right? And we're supposed to find in the neighborhood of a point. So the point we're looking at, what was it? It was pi over 4, 0. And we're supposed to find the path followed by a heat-seeking particle that originates from the center of from that point, right? So what's the idea here? So here's the context, right? Just put it in a box. Here's the point, pi over 4, 0. And the gradient vector field looks something, I don't know what it looks like exactly. Here's maybe the gradient vector field. I don't know what it looks like exactly, but maybe it's something like this. Okay, here I'm plotting the gradient of t. If that's the gradient of t, then what are the level not surfaces here? What happens if you set t of xy equal to a constant? You don't get a level surface, you get a level curve. Yeah. So the level curves, right, they're looking something like this, right? See, here's level curves of t, right? Something like that. And we're asked to find the path a heat-seeking particle will follow, right? So it seeks the heat, right? It seeks the direction the temperature is increasing the most. So basically, you're looking for the path which lines up with the gradient vector field. So if I could plot that path, you're looking something that kind of like connect the arrows and connect the dots. Something like this is the path we're looking for, heat-seeking path. So the heat-seeking path would try to follow the gradient to the higher temperatures, right? So okay, now if we let say r of t equal to x of t, y of t to suppose that's the heat-seeking path, then what equation do we want? We want something like we want the gradient of t at r of t, right, to equal what? So think about it. You want the tangents to this path, right, which would be like r prime of, this would be r prime of 0 if we make this r of 0. It suggested we do that, right? So what do we want? What equation do we want to have the heat-seeking particle solve? I mean, you could put a scale factor here, but basically we want the gradient vector field to match the velocity vector field along the curve. So you want to solve this is equal to dr dt is what you want to solve. Now what's the gradient of t here? Let's see here, square root of 2, right? I'll leave that out front. And what you got is a minus, I could have been greedier, I could have left the exponential out front. But I got minus sine of x e to the minus y, comma, looks to me like minus e to the minus y cosine x. Again, to be greedier, I can do square root of 2 e to the minus y times the vector minus sine x minus cosine x. Oop, I see I could have been greedier still, but it's too late. A couple of minus out, right? Okay, so that's the gradient, right? And so what I want to do I want to try to solve this, right? So that would be something like, let's see here. Well, I'm not sure pulling the square root of 2 and e to the minus y out was actually helpful. Let me put it back in. Sorry. Sometimes it's helpful, sometimes it's not. Here I don't think it's going to be. So I'm putting the square root of 2 back inside the gradient just to be, I think it's going to be more helpful to do this. We'll see in a second here. So that's the gradient, all right? And I'm thinking here x and y being the functions of time that we're trying to find. right? Your goal is to actually find x of t and y of t if you think about it, right? That's what we're doing. We're trying to figure out what is x of t and y of t to find the heat-seeking path. So this would be dx dt dy dt, right? Because that's that. And so what do you got to solve? You got to solve dx dt is equal to minus the square root of 2 e to the minus y sine x, and dy dt is equal to minus the square root of 2 e to the minus y cosine x. Oh, I'm probably being too greedy. Yep.
I just wanted to clarify for problem 33, on the mission of square root of x squared minus y squared.
But we're not to that. I'm not done with this yet, so you have to wait until I'm done. I'm sorry. I mean, that is next question. So it's like confusing me. Don't do that. You overestimate my processing power. This one requires some amount of my processing require. So past here, I mean, I don't know. So to find the exact solution, I'd have to solve these two equations, right? Can we do it? Yeah, actually you can. What you do is you just divide the one by the other. This gives me dy dx is equal to those cancel, and you're left with like cotangent x. And then the integral of cotangent is something like y equals natural log the absolute value of cosecant of x plus a constant, something like that. I might need a minus there. I'm trying to think. Derivative of, so get 1 over, oh, not cosecant, it's 1 over, excuse me, integral of cotangents, like it's cotangents cosine over sine, so it would be like sine. That's a something like that, and then I just pick the right value of c. That would give me the equation of the curve, which lines up like this. I eliminated the time by dividing the differential equations. Now, it may be what we're asking for here, maybe what the book wants for here. Does it just have like a line in the back? It's an odd problem, right, when you look at the answer?
Yeah, it gave
Does it give you a line, or does it give you like a parametric? Just a line, okay. So all they did was what? They were less ambitious. Like I tried to find not just at the point, I tried to find local to the point a curve which lines up with the vector field. They're less ambitious. They're just like, I'm going to solve it just at that point, right? Just at that point I can do easier. The line which you want would be L of t, would be the point which was pi over 4, 0, plus, say, times the gradient of t at that point, right? And that infinitesimally will give me the heat-seeking path. The trouble over there, what I'm doing is trying to find it more than just infinitesimally. I'm trying to find it like further out, which is unnecessary for this problem. Okay, so that's pi over 4, 0 plus t times the gradient at pi over 4 is what? Minus 1 minus 1. There you go. And that's the answer, right?
No, they keep going with that.
Oh, they do?
At least in mine. Yeah, I mean, that's pretty much what they get, except it's root 2 sine x. That's what they get.
Which one were we? We're 16.2.
To
Number 37. Oh. Aha. Hey, how dare you? No. Okay, so there's a square root of 2 that I lost somewhere, but yeah. This is approximately how you do it, though. That's the idea. Yes, sir.
So that line is the direction of
Yeah, this would be the, basically just follow the direction of the gradient. That would take you to the higher, like, just at the point. If you just want the direction that you'd be traveling, this infinitesimally is the answer. Something like this fixed up a little bit is the more sophisticated answer. Now, I told him I'd answer his question next, which was what's the deal with the UXX and U of VV or whatever it was. So another way I could have asked that, which number was it?
No, it was just for 33 if it was actually equal to plus or minus.
Then it goes between x squared minus y.
Oh, this? Oh, yeah, minus. Sorry. It's no fun if it's plus. Wait. Yeah, minus. I'm sorry. Oh, that was a totally legit question to ask me earlier. I thought you were asking me about the question Luke was asking about before class, which would have been inappropriate. Except that Luke asked me before class, which was fine. All right, let me stop talking about proper classroom etiquette and start actually answering your questions. So the other problem, I had to show u equals to, what was it?
E to the power of x cosh y.
Ex cosh y, and v equals e to the x sinh y, to show that these were solutions of uxx minus uyy equals to 0. Now, I could just as well have written this instead. I could cross this out and replace this with, say, phi xx minus phi yy equals to 0. Or, if you want me to continue this silly discussion, I could have written this. So what does it mean to show something's a solution to, let me give it a name, these differential equations? What does it mean for something to be a solution to an equation? Yeah.
Just find each one.
See if they make 0, right? So what you're saying is I should plug it into the equation and see if it actually is true. For example, here's something that's not a solution. If I was to say phi of xy, or sorry, keeping with my point, if I was to say u is equal to x cubed, suppose I was to say that. That would not be a solution, right? Because if I calculate the second derivative, I get what? You're like, well, with respect to x or y. See, this has what? Uxx equals to 3x squared 6x. And it has uyy equal to 0. So obviously, if I take the difference of 6x and 0, I don't get 0. In fact, it's not true that uxx minus uyy is equal to 6x, right? It's not equal to 0. So in other words, therefore, u equal to x cubed is not a solution. So you have to show the opposite thing, which is that if you perform the indicated differentiations, it works out. It's a solution. Yes, sir?
This to be plus.
Oh, sorry. Yeah. I was thinking of something else. I changed equations mid-thought. Sorry about that. So next question. Mm-hmm.
For 38 part B, talk about,
Oh, yeah, 38 part B.
well, I call it part B. Second part where you're trying to find L and show what the relationship is.
Uh-huh.
Sure how to go about it.
So find a parameterization of the line with that direction and feed it to the function. That should give you a function of one variable, right? So what special property does that function of one variable have? That's the question. So like I said if L is a line through 1, 2, which is perpendicular to the directions through which you get maximum and minimum rates, right? So I guess there's two possible directions for L, right? I don't really care which one you do. You could do either one, it'd be fine with me. What special property, do you observe for f of xy when xy is an element of L? No. So in other words, you could attack my question in the following way. I mean, I'm just recommending. The question is, there's a couple different ways you could answer that, but here's one way. If you had, R of t, parameterizes that L, right? Then you could look at f of R of t and then see what happens with that, right? if I call that the g of t, and suppose r of suppose r of 0 is the point in question. What was the point? 1, 2? You could say, what if this is g of t? What can you say about g of 0 is what? Or, well, I mean, I really can't say much more about this question. I kind of already answered it in class before. Well, there's not a lot to do here. It's like maybe 3-4 lines. Other questions? Yep.
Can we do a problem similar to 34?
Yeah, 34, the tough thing about 34, and it's kind of the tough thing about 33 too, right, is inequalities. Or when are things 0, right? So, one of the homework questions you have, and I'm gonna get to your question, but first let me just talk about, I think it's 15.1, the first question, right? It's kind of related. It's, you have f of xy equal to the square root of xy, and the question is, what's the domain? How do you figure that out? If a domain's not explicitly stated, what's the convention? The convention is you're greedy, right? Greedy as you can be. Try to make it as big as you possibly can. So when does this formula make sense is essentially the question. You need what? Right, exactly. X times y is non-negative, so greater than or equal to 0, right? And so if you think about that, that means either both x and y are non-negative, or they're both non-positive. So I can graph that. So it's basically this, right? So that's the domain of f in this case, right? Now the question you asked me about, 34, it's kind of similar. It's some kind of crazy fraction of things. And the question more or less is, when does that limit exist, right? So certainly the limit exists everywhere where that formula makes, if you could just plug in a comma b into the formula and you don't have division by 0, you're good to go, right? It's a rational function. So that's really all you got to worry about. So the question then really for that problem is, when can the denominator be 0 for 34? That's really the heart of the question, right? So there's something technical there that is kind of tough. I'll help you guys with the algebra a little bit, since it's a little bit hard, I think. So let's see here. I'm just going to focus on the difficult part. Let's talk about the limit as x, y. So I'm going to do a very related problem. X cubed plus y cubed. All right, it's very, very related, right? So when does this limit exist? When does it not exist, right? That's the question. Sorry for doing one so much like your homework. I really should come up with one which is more different. But this is the heart of the matter. So really the question is, when can x cubed plus y cubed be 0, right? If x cubed plus y cubed is not 0, we're fine, right? So like, I would just say that this is equal to 1 over a cubed plus b cubed, provided what? Not equal to 0, right? Because the limit laws apply. We can just plug it in. Good to go. So how do you figure out where x cubed plus y cubed is 0? How about this? It's a difference of cubes, right? You can factor it. How? How do you factor it is the question, right? I think this will work. X plus y. And the reason I say that is if you think of y as being a constant and think of x as being the variable, if I put x equal to minus y, right, then I've got minus y cubed plus y cubed, which is 0. So minus y is a 0 of the polynomial if you think of y being a constant. So that means by the factor theorem, I got to be able to factor out x plus y. Anyway, the proof is in the multiplication, so this is x squared. This has got to be y squared. What goes in the middle? I guess there better be a minus, otherwise we're in trouble. Does that work? Why do we factor things? Anyway? What's the point in factoring? What does it get for you? Yeah. Exactly. You're like, but I had one problem, now I have two, but that's the good thing. You have one complicated question you don't know the answer to, now you have two slightly less complicated. Well, one is really not complicated at all, right? When is this 0? Yeah, well, I guess I'll use y. Y is equal to minus x, trouble, right? So definitely this limit does not exist along the line y equals minus x, right? That's out. The question is there anything else out, right? That's the technical question. This much I don't think is technical. What follows is technical. So the question is this 0? So I'm going to share with you a fun fact of linear algebra. Fun facts are those ones which we don't have to prove, which you will accept because they are truths from the great beyond. So here's a fun fact. If you have ax squared plus 2bxy plus cy squared, all right? Let's call this thing q of xy. In fact, this is what's known as a quadratic form in two variables. You can figure out whether this is positive or negative, how the story goes, by looking at something called the determinant. So what you do is you look at the determinant of a minus lambda, b, c minus lambda. All right? So what is that? That gives you what? That gives you lambda minus a times lambda minus c minus bc. That's a quadratic equation. It turns out, by something called the real spectral theorem, that this has real solutions. All right? It is an inescapable fact of mathematics that this will have real solutions. If I set this equal to 0, I can tell you that there are going to be solutions. Lambda 1 and lambda 2 are in the reals, and those are the solutions. Those are, in fact, the solutions to this equation. More than that, I can tell you that you can rewrite, all right, you can rewrite q as equal to lambda 1, and I need some other language. Let me just say alpha squared plus lambda 2 beta squared. So there's some like substitution you can make. Let's say alpha and beta, which are functions, simple functions of x and y, all right? So what is this? I mean, so what? Well, if lambda 1 and lambda 2 are like both what? If they're both positive, or if they're both negative, then you know that there's no place where it's 0. Because there's no way you can have a sum of two positive things squared, and there's no way you can have a sum of two negative things, strictly negative things, that cancels out and gives you 0, right? On the other hand, if one of the lambda 1s is positive and one of them's negative, or if one of them's 0, then you have a 0. So this is like a theorem. So if I apply that to here, see what I get. is 1 minus lambda minus a half, 1 minus lambda. And if I calculate the determinant of that, I get lambda minus 1 quantity squared plus a fourth. Oh, excuse me, minus a fourth equal to 0. I mean, setting it equal to 0 is what I want to do. But let me just, you can factor that. That's lambda minus 5, let's see, that's 1/2 squared, right? So this is lambda minus 3/2 times lambda plus 1/2, well, minus 1/2. Long story short, lambda is equal to lambda 1 is 3/2 and lambda 2 is 1/2. Which means that I can make a substitution which takes this x squared minus xy plus y squared and puts it in the form 3/2 times something squared plus 1/2 times something squared. The good news is, in fact, that term has no places where it's 0. Now, how should you attack this? Because you don't know fun facts ahead of time. While you're waiting for me to tell you these sorts of things, how should you approach this kind of term when you come to it? You have many tools at your disposal, right? You can use Wolfram Alpha. You could plot it. You can use Mathematica, MATLAB, whatever. You can just graph x squared minus xy plus y squared, see what it looks like. In fact, what it is an ellipse. It's a twisted ellipse. So if you look at the level curve x squared minus xy plus y squared, it's something like that. I'm not sure which direction it's rotated, but it's just a rotated ellipse. And so it never crosses the origin. There's no place where it's 0. Long story short, the only place where the limit doesn't exist is y equal to minus x. That whole line is gone to us. Everything else exists. So what was the hard part? It wasn't the calculus, was it? It's the algebra you don't know that'll get you. Fortunately, this time, you can take solace in the fact it's not algebra you forgot, it's algebra you haven't learned yet, right? So it's not a bad thing. See, that's the thing, is you don't really have the technology yet, most of you in your education, to deal with expressions like this. Things that have mixed terms, it's outside your current bag of tricks, right? That actually you need the theory of rotations. You rotate coordinates and it will change it to a coordinate system where it's just sums of squares, where things are easy to understand. This is something you learn in linear algebra, ideally. Okay, there must be other questions. Is that so you see what they do for that one then? I mean, there's other stuff there, but for example, the x minus 1, there's a square in the denominator. The x minus 1s you could kind of like reduce. If you have a leftover factor in the numerator, you get 0, right? If you have a leftover factor in the denominator and there's nothing to counterbalance it in the numerator, game over, just like in Calculus 1, right? So the usual terms and conditions apply for figuring out limits algebraically. Yeah. Someone else, yeah?
Problem 38, finding the minimum. Is that just a negative of the maximum, or? Oh.
In terms of direction, yeah. And actually, both in terms of direction and in terms of value. If you go in the direction of the gradient, you get the maximum value for f. The maximum rate of change, right? If you go opposite the direction of the gradient, you get the maximum negative rate of change. And it also is minus the positive rate. Yeah. Yes, sir.
All right, so you said the minimum and the maximum of that problem have opposite directions. Is that right?
As long as I'm not so foolish as to have picked a point with gradient 0.
Okay. Then
No, I
is
didn't.
there any single line that is perpendicular to both the minimum and the maximum vector?
If you take a line in 2 dimensions, is there one line that's perpendicular to
Or
it?
just 2 dimensions?
Yeah. Oh, yes. If it was a three-dimensional question, it would not have been as friendly. Then there's a perpendicular plane, right? There's a whole level, there's a whole tangent plane, which is constant. Yeah. I could try. Yes, thank you for asking about that. The other thing I wanted to mention before I forget, I asked some questions about the total differential, but you guys haven't even had a question about that. So by that I gather that you realize that the definition of df, right? So it's either partial f partial x dx plus partial f partial y dy, or if that's in for R2. Right. I will answer your question eventually. I have to get this out of my system because none of you asked me about this yet. I never defined that in class, right? But this is called the total differential of f. What is it? Well, that's a good question. What is it? For us, at the moment, it's just a formal symbol. You can use it as a mnemonic for how to approximate things. For example. If I had f of let's say x comma y equal to, gee, I don't know. What do you want from me here? How about say again, sine of, okay, square root of x plus y squared? Okay. That's not what I want. I don't know. I can never come up with a decent example of these stupid things. All my examples are stupid. I'm trying to think of something with x and y that f has a nice, how about this? How about if I have a box that has height y and it's square, right? What would the volume of this box be? Yeah, x squared y would be the volume, right? So if I were to tell you that you have an uncertainty in the measurement of x of about 2 inches, and if I was telling you the uncertainty of y was about 3 inches, then you could ask, how uncertain are, and suppose that x is equal to 10 inches, and suppose that y is equal to 20 inches. Then you could say, okay, so what's the volume and how certain are you of the volume? Would be a kind of standard sort of question you could ask. Well, this differential gives you a quick way to estimate that. So basically here it is, df is equal to 2x y dx plus x squared dy. And so the change in f is approximately, it tells you the pattern. The change in f is approximately 2xy change in x plus x squared change in y. There's a better answer to what the total differential is, but that comes later, and so I won't burden you with that right here now. So you got 2 times, what is it, 2 times 10 times 20, which is what? So I got 400, and the change in x I said was 10, and then x squared is 100, and the change in y I said was 3. Oh, it did? Oh, thank you. Yeah. What am I saying? And then, so what's that? Looks like 1,100. 1,100 inches cubed. So the uncertainty in the volume is about 1,100 inches cubed, even though the uncertainty in the x measurement and the uncertainty in the y measurement is just 2 inches and 3 inches respective, because, well, if you think about it, you're going between what? Between like 8 inches and 12 inches in the x, and you're going between like 17 and 23 inches in the y, if you think about it conceptually. So there's a big difference in those volumes. But I didn't actually have to calculate the absolute change, because I can use this differential to approximate the error in this way. It's really just a shorthand for replacing the nonlinear function with linearization. Now let me get back to your question. So your question is something like this. Given a function of 3 vector field, right? And I don't know, how about this? Let's see here, x cubed, yz, oh man, let me make that a 2yz, y squared plus e to the z. There we go. That's weird enough. So here's the vector field. I just made it up. And the question is, can you find another function, little f, so that the gradient of the little function, the so-called potential function, is equal to the vector field? That's the question. That's 45, right? So how do you solve such a problem? So if you look at it, what you got to do, I mean, I haven't taught this to you guys yet, so I'm basically challenging you to think through it and try to figure it out for yourself, but you know, that's why we have these days also. So let's see here, partial f, partial x, partial f, partial y, partial f, partial z, right? That's the gradient. So I have to solve 3 equations at the same time, right? So look at it. I got to solve partial f partial x equals to what? X cubed. I've got to solve partial f partial x equal to what? 2yz. I've got to solve partial f partial z equal to what? Y squared plus e to the z. Now, I should warn you, it's very dangerous for me just to write down a vector field and hope we can do it. There are many, many vector fields, infinitely many in fact, which is simply not possible to find the function f whose gradient gives you back the vector field. Oh, that's not good. There we go. So, I mean, if this is possible for a vector field f, it makes it a very special kind of vector field. Such a vector field is said to be conservative. It corresponds to like a conservative force field, one for which there's a potential energy function. This little f we're finding is essentially minus the potential energy for the force field. But, you know, how would you solve such equations is really the question, right? Right? That's the right idea. Partial what, though? I mean, I want to call it a partial integration. No one says that, right? But I'd like to say, like, integrate over partial x for the first one. What would that give you? Sorry, I'm trying to find my red. Oh, there it is. What'd you say? Yeah, so like basically integrate. So what I'm really saying is anti-differentiate while treating y and z as constants, right? So here's the subtle thing. This means that we have f equals to 1/4 x to the 4th, right? Plus some constant, c1. Now, that's not just an ordinary garden variety constant. That constant could be a function of y and z, right? So, but this is the first step on our road to making a properly educated guess. Okay? I mean, so look at this problem. It's a question of integration. What is integration at its base? Integration is guessing, right?
Shouldn't that be the integration of partial y?
Ah, man. Again, this notation I should put quotes around because it's not, it's by no means, a publisher would never let me get away with this, you know. Whoa. You're very brave. Have you looked up? Integrate this with respect to y, what do you get? Y squared z plus c2, possibly a function of x and y, right? Because here I'm holding, oh, I'm sorry, I'm an idiot. X and what? Z, right? Because I'm holding x and z fixed in that integral. And then finally, what do you get? The third one? Let's see here. Integrate with respect to z, I get plus possibly some constant with respect to x and y, right? And then what you do is you think for a bit, and you write down the answer. So the answer apparently is 1/4 x to the 4th plus y squared z plus e to the z, and then plus any constant, honest to goodness constant you like. There's always a freedom to add a constant because the gradient of a constant is 0. Now, some of you have the question, why isn't it 2y squared z? Why do I just have one of those? I found 2 of them, right?
When you partially integrate in y and z of the y squared z, you come up with those 2 different answers.
Right. Those are from the same source. I mean, yes. Of course, that's the danger of this method, is you can get tricked into lumping, putting 2 things. Also, another danger is you could write down an answer which is total nonsense. Let me show you how it fails. Here's a 2-dimensional example. F of xy equals to minus yx. All right, so I got partial f, partial x equals to minus y, partial f, partial y equals to x. This gives me f is equal to minus xy plus c1. This gives me f is equal to xy plus c2. So I'm like, okay, so apparently f is equal to c. Or no, f is equal to, I don't know, what would you do? Why won't it work? See, now I can't make sense of it, right? Just because you can do these partial integrations doesn't mean they're going to work. See how this one breaks down? Like, what? I don't know what to do there. Right, yeah, in fact, there does not exist f such that f equals to the gradient of f here in this case. That's right. That is not a conservative vector field. It's not like gravity or electrostatic force or spring force or other fun stuff. Other questions? Were there fun problems in the book? So many fun problems. You guys asked me about the hard book problem. There were so many easy ones I could have done. Oh, man. These are mean to me.
Well, you don't need help with the easy one.
Oh, okay. Fine. You have a good point. All right, with that, I will shut up and let you go. See you guys tomorrow.